Thank you. Thank you for introduction, and I'd like to thank James and Ankit for putting together this very nice workshop, which I'm enjoying. You see the title of my talk, I changed one word in it to be a bit more general, especially after hearing all these general questions which James put in very first talk. We want to know a lot of things. We want to know how to control some photo-induced states. We want to know how to use these photo-induced states, so I put TMDs, but in reality I would talk about single TMD, which is 1T-tantalum disulfide. Unfortunately, that's where we are now. We know that it works there, but hopefully we can find also other systems where it would work. Anyhow, I'll present some metastability in a sense of human time scales. So we are here not very interested about very short time scales, but we are interested in something which is minutes, hours, or years. And a very brief historical introduction for those who haven't heard about this material yet. You saw this image in Martin's presentation. So 1T-tantalum disulfide is charge-sensitive material, and at low temperature, it's believed to be mod insulator. At least it was. People were sure about that for quite some time before some discussions about band insulating behavior appeared. But anyhow, from purely experimentalist point of view, who put the electrodes on a sample and measure resistivity, it is clearly insulating. And then after we expose it to a single laser pulse, the resistivity drops a lot, and it gets to this value. So we can induce some insulator to metal transition by a single laser pulse. And that was observed like 10 years ago, and since then we are trying to understand what we are actually doing. So just very brief introduction of the states which are involved. So at ground state of the system, as I told, is charge-density wave state. This CDW causes a lattice deformation, which looks like this Star of David, and in the center of each star there is sitting one electron, and those class structures are tiling the whole surface of the sample. So that's what you would see under STM. Now, if we shine the single laser pulse on it, we produce some textured phase, which again has some domain walls in between, but that's what we see. And this state is obviously quite stable, but fortunately or unfortunately, this is not everything we can get in the material with after the photo excitation, and this is now fashionable in the field. We can extend the phase diagram beyond, let's say, temperature, pressure, and we can add another axis of photo excitation, or here I call it fluence, or photo doping, as you wish, and we can actually observe a lot of different states. So here, only those two are thermal states. So the C state, commensurate state, is the insulating, which I just introduced. At room temperature, the material is is conductive, so that's NC state. This H state is the textured phase, which I also just introduced. That's this one. But if we apply a bit stronger pulse, we can also reach something new. Like, for example, this kind of glassy state, which you also might have noticed in Martin's presentation at higher fluence. And if you zap the sample even more, we can actually create a lot of different things, like polytype transformation, some other stripy orders, but I will not talk about those today. I'll mainly focus on the first two, so the H state and A state. Both are pretty stable, and both are quite unusual. And so right after observation of those states, a lot of questions arise, so I'll try to answer one by one. And first, and probably the most frequent question was, how fast is this? And here we were actually pretty lucky to be able to measure how fast the transition is, because in this case I'll talk about this textured phase. It has nice fingerprints in any kind of measurement we are doing, including the optics. And we can observe in simple palm probe, we can observe the coherent oscillations which are coming from breathing mode of these polarons. And those are changing the frequency once we are going through the phase transition. So in multi-pulse experiment, what we can do, we just start our palm probe, we induce the oscillations, and then where this D is the switching pulse comes, and the frequency of oscillation is changing. So now, by looking in details, what is the frequency on this side and on this side, we can narrow down the region where some dynamics is happening, and it's this shaded area here with a width of just a half a picosecond. So the whole change occurs within a half a picosecond, which is kind of cool and pretty fast. Anyway, for now, that's it about the speed. I'll talk a bit more later. But the next question, which is interesting both fundamentally and probably for some kind of practical application, if you want to use switching between an insulator and metal, why it's conductive. But here we unfortunately first have to go a step back and find out why the ground state is insulating. And that's what I just briefly mentioned at the beginning. I don't think we do have good answer for that. So there were some ideas that it might be mod insulator, but then some calculation appeared that if we just freeze these polaronic deformations in plane, and in DFT, if we only change the way how they are stacked on top of each other in out-of-plane direction, we can get a lot of different properties. I mean, starting from the insulator to out-of-plane metal or just completely metallic behavior. And the in-plane structure is completely frozen here. And indeed, in the experiment, this restacking was observed. For example, here is some X-ray data for two different states. So conductive thermal state, high temperature state, and the insulating state. And indeed, those two curves, since they're not overlapping, I'll not go into details, but this means that there was some kind of restacking. And indeed, the low temperature phase is now believed to host those dimerized layers, which from the calculation seems to give the insulating behavior even without any correlations. Anyhow, I don't want to talk if it's mod or not mod. I guess there are many people in the room who knows it much better than I do. But what I want to point out here is that it's definitely something which we have to look at. So what is the stacking it? And the problem is that in many of our probes, we are not sensitive. So we did a lot of STM, but that's kind of what I would call flat earther's view on the system, because we are looking only on the top layer. However, it appears to be not always the case. And in some cases, even in STM, we can see what happens a bit deeper. And here is one nice experimental example. So we can go to some edge of the layer. And because, if we believe there is this dimerization, depending how the sample is cleaved, we can either cleave it so we destroy the top dimer, so we cleave the dimer in half, or we can cleave the sample such that the top dimer is still intact. And according to the calculations, that should produce quite different spectrum. And that's actually what is observed in the experiment. So what was done here, they did tunneling spectroscopy along this line, and you see going through the steps, so going a bit from what's this called A termination to L termination, so between the dimers and cutting the dimer in half, you can see that there is huge modulation of the gap. So indeed, it is important. And this actually poses another question. So what we observed was this hidden state in the surface. So is it the state which occurs only on the surface, or is it a bulk state? And then second question is, what is the stacking of the hidden state? Is it similar to the high temperature, so what we would call conductive stacking, or is it also the dimerized state? And answering the former question was actually pretty easy, because we observed the hidden state in any kind of probe, including optics, and optics is quite bulk sensitive. So we know that it is bulk. Answering the second part is a bit trickier, but also there is this nice work which did X-ray diffraction. And here, this low temperature insulating state is characterized by the additional peak, which is due to dimers, which is absent both in thermal high temperature state and also long time after the photoexcitation. So it seems like restaking does take place. However, this is a static experiment. Now we want to do it dynamically, see what is the dynamics of this thing is, and for that we did electron diffraction. The reason for that, I will not go too much into details, but basically because here in a single experiment we can really observe everything we want. We don't, with X-rays, usually there are much more troubles to see the parts of brilliant zone which we want. Here we see everything. And that's why no, that's another, okay. So that was actually done for thermal states on 1T disulfide. And here are some cuts of of the diffraction patterns for 2 different insulating and metallic states. And yeah, hexagon is a Brillouin zone, so you see some charge density wave satellites around, which depending on the state, which might be brighter at this L projection or at different L projection. So it's indeed a good probe for testing our state. And that's what we do, but with the time resolution. And here is this, I think, the ugliest slide you have ever seen, probably. But I guess it's the good way to show what we want to see. So actually, it seems like it's still too large. I probably had to squeeze it a bit more. So here one image is just the differential diffraction pattern. So pumped minus unpumped for different times. And of course, before time 0, there is nothing. Then at around time 0, a lot of things appear, which are then more or less static up to the longest time delays of 100 picoseconds. So why I've squeezed it so much? Because I don't want you to look at the details, but I just want to, okay, maybe you still need to defocus a bit. And you'll see that there is some, in each pattern, there is a bluish band, which is almost horizontal in the center. Let's say somewhere here. And if you go higher or lower, it's something more reddish. And that's exactly what we want to see, because here in these patterns, along the vertical axis, what we have encoded is out-of-plane staking. And the fact that the behavior is changing as we go along the vertical axis, that means that staking does change. And now we have to look into more detail. So here is larger image. I again can draw the Brillouin zone, and in the center of each hexagon, you have the bright red spot. That's a Bragg peak, which simply goes up because we are partially suppressing the charge density wave. So of course, Bragg goes up. Now, if we try to look what's happening with the charge density wave, first I can use all the spots we observe and plot some kind of basically L-integrated dynamics. So this way we don't care really what the staking is, but we are mostly looking on something similar to STM, let's say. So we are just sensitive to this amplitude of charge density wave modulation in plane. And you see the dynamics, which is also pretty fast, and of course with opposite sign to the Bragg spot. What's interesting is that despite very strong pumping, we never really completely suppress charge density wave, so it drops by maximum like 30%, and then it quite quickly recovers to almost 80%, and it settles there. So it's quite different from all this kind of more thermal transitions, where you first have to completely suppress the order, and then something reappears back. But we are more interested in something different, so we are more interested about the staking. And here is this pink curve, where I just took some satellites which are aligned to the staking, which is characteristic for this insulating behavior, and divided by staking, which is characteristic to the metallic behavior. And the fact that it goes down indeed means that the restaking occurs, and indeed we are reaching something which is similar to the thermal conductive state. This happens on pretty fast time scale. You can see it's one picosecond or so. Interestingly, it's actually non-monotonous behavior. So there is first some kind of transient increase of this dimerization, and only then dimers are getting destroyed. I don't think I can comment much more on that, because currently from this data we don't have anything more. But it just highlights some unexpected and probably interesting behavior. Anyhow, now we can do the fluence dependence. So here I'll show just some constant delay, or actually it was done in a static case. As we increase the fluence, okay, so those are millijoule per square centimeter, we observe very similar patterns as on the left. So with some bluish band in the center and something reddish around. But once we get to the higher fluence, except increasing of the contrast, what we see is that the whole pattern gets much more ugly. So there are no sharp spots anymore, but there are some streaks all around the Bragg spots. And the reason for that is because that's where we are reaching the second state. That's this amorphous, what we call amorphous state. And this one, as you can see already from STM, is much more disordered. And actually, this one does not have any preferential direction, and that's why what you would see instead of these 6 satellites around the Bragg spot, there will be just a kind of hexagon. And that's why we don't see any sharp peaks anymore. Unfortunately, that's the one which we are more interested in now because we don't understand it, but unfortunately it's also much harder to study it because it's disordered. It doesn't have any such nice fingerprint as the first state. For example, in optics, we cannot see any coherent oscillations because it's disordered. It's also conductive. The conductivity is pretty similar to this H state, so we cannot measure it just directly by measuring the resistance. So we need some probe which is either microscopic like STM, or we need some diffraction experiment, which is doable but tricky. And so for now, the only thing which we probably can at least somehow roughly measure is how stable this state is. And at least we can compare it to the stability of the hidden state. So for that, we tune the experimental conditions such that the hidden state is now, I mean, I didn't talk about it a lot, but by adjusting the temperature, we can tune the stability of the hidden state a lot. And we can go to some temperature range when, let's say, the hidden state survives for, okay. I have to be faster. Anyway, we can tune to the conditions where the hidden state doesn't survive for long. But still, if we continuously pump, we'll see it. And by increasing the fluence, you can see this increase of conductive staking, let's call it this way, and decrease of insulating staking. But once we cross this 8 millijoule per square centimeter, something else is happening, and basically charnist wave gets suppressed a lot, but it is still there. The staking order apparently getting destroyed. What more interesting things occur when we stop the pump, because now the hidden state disappears in a few seconds, so we don't see it anymore. So we are here in this state, but this suppression is still there. So this is in a static case already. This was, I think, done at 120 kelvins, and apparently at this temperature, this glassy state is much more stable. It's still a question whether we can reach this state at higher temperature or not. Since I don't have a lot of time, I will not go too much into details, but I want to show another experiment which very quickly, which I think is interesting. And it really, if you still don't trust that it's non-thermal state, I think that here you will trust it. So this transient grating, how it's done, you just cross two laser beams, you produce interference pattern on the substrate, on the sample, and measure diffraction from this interference pattern. And usually it's done for a lot of different things, but we want to use it in a slightly different way. We want to create this periodic pattern of different states on a substrate. So in the bright stripes, we'll induce this hidden state, and dark stripes, it should stay untucked. And if it is a thermal transition or somehow related to the heat, of course, once the whole sample is thermalized, this photonews or hidden state would also grow to the whole sample, or it will completely disappear. So in any case, diffraction has to be removed. And first test experiment at room temperature, where we don't expect any long-lived states, and it actually does behave normally as a transient grating experiment. I will not go again into details here, but what's more interesting, if you cool down where we do expect photoinduced states, and we start our pump beams here, we start to see some diffraction, and then it slightly relaxes, but it stays almost constant. What's important here is that time scales are now in the seconds. So while here we were doing something in stroboscopic regime with few, I don't know, after 200 picoseconds everything was relaxed, here it is stable. And in fact, it was done in real time. So here, after this point, the pumps were completely blocked. So indeed, this photoinduced state does not grow into the dark stripes. Of course, that's quite frequently happens if you burn the sample. So to see that we did not burn, we open just a single beam here. So it doesn't produce any diffraction or interference. It just acts as a kind of heating. And you can see that you can completely recover the sample and repeat the whole thing many, many times, it always works. Interestingly, the intensity here was unexpectedly high. Okay, I didn't scale them correctly, but this one at least 20 times larger than what's observed at a few picoseconds, and it's at least 1 order of magnitude higher than what's usually observed in this geometry. And to understand that, we have to actually check what's happening with the lattice, because this was extreme UV transient grating, which is not very sensitive to any electronic properties. It's mostly sensitive to really lattice modulation. And if you try to see what happens with the c-axis, lattice constant along the c-axis, already by going from the room temperature state to the low temperature state, there is a huge jump of about 0.5%. And yeah, for heating state, we do not know what exactly the lattice constant is, but because it's so similar to this high temperature state, we probably can expect some kind of similar magnitude of jump. And that's why we actually have to look not like this on our geometry, but more like we have to see what happens with the profile. So, and there apparently the real space modulation of the surface occurs. And that can be very easily calculated. We just take some textbook formula for sinusoidal diffraction grating. We can calculate it for different wavelengths, different angles, and this solid black line is our experimental wavelengths, and our experimental diffraction efficiency is a star. It actually matches unexpectedly good. And why I thought it's interesting, not also from practical point of view, because by tuning this geometry, let's say going to slightly shorter wavelengths, slightly increasing the modulation amplitude, and going to the grazing incidence, we can reach the diffraction efficiency, which is of the order of few percents. And that's not a lot for optics at all, but this is in X-rays. And that's a few percent is the diffraction efficiency of edge diffraction grating for X-rays. So here we have some modulator which can be tuned on the picosecond time scale and has efficiency of the edge diffraction gratings. Anyway, now I don't have time apparently to answer the question why it's so stable. So that's for next time. I'll just go directly to acknowledgement. Yeah, most of the work was done at Jozef Stefan Institute. UED was done at SLAC, and transient grating at Electra or at Fermi free electron laser. And I wanted to finish. A few days ago, we heard that the life exists only out of equilibrium, so I wanted to show that our sample is actually alive. This is a STM image, real-time STM movie of the surface of the sample with about 3 frames per second. And here you can see this top part is a hidden state, so this textured phase, which we just saw with some domain wall here in the center. And the bottom part is more like this amorphous or glassy state. And you can see that actually there is a lot of dynamics happening also on time scale of seconds or milliseconds. So apparently the sample is trying to find its path or explore its free energy surface, trying to find the global minimum, or actually, I don't know, are we trying to find the global minimum or we are trying to avoid it? Anyway, thank you.